Morning, everybody, and welcome back. So yesterday, we ended our discussion of the full configuration interaction theory. And we started with outlining the Hartree-Fock approach, which is a so-called mean field method. And as we mentioned yesterday, this is something you can consider as a kind of kitchen item. You always run a Hartree-Fock calculation first in order to get a hopefully better single particle basis and also a better ansatz for the ground state energy. And this better, supposedly better single particle basis is something which may speed up, one, the calculations in full configuration interaction theory, or the convergence of other many-body methods, which often are rewritten either in terms of a perturbative expansion or the resummation of specific terms. So Hartree-Fock theory means that we define a single particle basis. We are going to use variational calculus in order to derive the equations. We are going to define a new Hamiltonian, which we will see reminds us or is actually equal to that operator F, the one-body operator, which we defined for a new reference vacuum. So Hartree-Fock, the hope is then that we can find a better estimate for the ground state energy. The variational principle tells us that this Hartree-Fock energy is larger or equal to the exact energy. And hopefully this is better than the one we had before. And what we are going to derive is the Hartree-Fock potential, so that we have essentially the basic methods which enter the calculation. And we are going to go through the basic derivations of the Hartree-Fock theory. Now, one thing I wanted to quickly remind you of, because we are going to use this, and that is a reminder on variational calculus and Lagrangian multipliers. So this is something which you probably encountered in one of the first mathematics courses you took at university. And probably a kind of problem which you met was a problem where you were to show that the shortest distance between 2 points is a straight line. I don't know if you've gone through that exercise, but that's a classic exercise you would meet in mathematics courses when you discuss the Lagrangian formalism. I guess you've seen these things before, some of them. I know that it depends a little bit on who teaches the courses in mathematics, but normally it would be for those of you who've gone at University of Oslo in Math 1100, this would be a typical place where a Lagrangian optimization problem would actually be, or variational calculus would be introduced. And as I said, the classic problem is actually to show that the shortest distance between 2 points is a straight line. And you can do that with variational calculus and Lagrangian multipliers. So the whole idea, and in our case, if you look at the energy of a specific system, this energy is now a function of an ansatz we have for the wave function or the state function. And this is normally called a function of a function. And what we are going to try to optimize is actually this function as a function of phi, which means that there is a function here which depends on the function itself, its derivative, and also the variable which enters this quantity phi of x. So this is a pretty standard problem in science, and it's not something which is limited to quantum mechanics. It's something which is widely used in tons of applications. I mean, as I mentioned, the case with a straight line between 2 points is one of the classic examples. And so the whole idea then, if we now look at a simple example, we consider now the quantum mechanical expectation value. And this is a very nice way, and it shows you the power of variational calculus, because you can derive Schrödinger's equation from the energy of the system. And you would do similar things when you take a course in classical mechanics and you look at the Newton's equation of motion from the gravitational force. That would be very similar to what you see here. So what we have, and these are the basic elements which you will encounter in the Hartree-Fock derivations as well, is now an expectation value for the energy in terms of the unknown trial wave function. And then we have a constraint that this wave function has to be normalized. And obviously also we assume that these are functions which define an orthonormal basis. And then we have a Hamiltonian, which in this case is just a simple three-dimensional one, or let's say one particle. Just as simple as possible. And then when you look at the variational calculus, there is one intermediate step here which is very useful. And we can rewrite the second derivative in terms of the products of two first derivatives, or the gradients here. And we know that when we calculate this quantity here, we know that this can be rewritten in terms of the wave function here times the derivatives. And what we are normally assuming is that at these two endpoints, the wave functions go to zero. And that the derivatives do not diverge. That's a basic assumption about the quantum mechanical wave functions. So that means that the first term here is something which we then can simply set to zero due to the assumptions we are making about the solution. Okay? And this has to do with the fact that we are using a probabilistic interpretation. So we move from a classical determinism to a probabilistic determinism, which is another way of stating the basic assumptions in quantum mechanics. So then, when we look at this equation here, what we end up with then, so I'm just dropping the limits here, is that we want to calculate an expectation value of this specific quantity here, where we have rewritten the kinetic energy, and we want to vary this. And so what we want is actually that a small change in this function psi then leads to a change in energy, which we want now to set to zero. So we have this constraint here, and it's common then to just lump together the constraint together with the function we want to optimize. And this introduces a so-called Lagrangian parameter, or Lagrangian multiplier. And so we would then have a function which looks, so this is our final function, so we have the derivatives. So if you go back to the original problem, which we set up, you have the function itself, and then you have the derivative of the function. So this looks like the standard entry definition of the Lagrangian problem. And then for psi, then we have use the Euler-Lagrange equations, which are the equations which follow from the optimization or minimization or maximization. And if we do that, plug in, this simply results in the famous equation, which we have here, which is Schrödinger's equation. So this shows you the power of the variational calculus, that you can use this starting from an expression for the energy and derive the equations of motion. So for those of you more familiar with classical mechanics, I mean, this is the same approach you would use to derive Newton's equations of motion. So what we are going to do now is to go back to the whiteboard, and we are going to look at how this is used in Hartree-Fock, or how to derive the Hartree-Fock method using variational calculus. So let's switch to the whiteboard. I hope this is something which you have seen before in one or another disguise. So the basic principles are the same for all kinds of variational calculus optimizations. So let's switch to the whiteboard and look at things in more detail. And what we're going to do now is actually to go back to the very beginning of the semester. And we are going to just remind ourselves of the wave function we started with, which is a Slater determinant. And then we're going to make a small change to that Slater determinant. Now you can make whatever change you want, but we're going to make a specific change. And this specific change has consequences for what we end up having. Okay, so let's quickly remind ourselves of where we started in the semester. So we call this for first quantization. And we made an ansatz for the ground state of the system. And this ansatz is given in terms of a Slater determinant. So we put a 0 just to indicate that this is now the ansatz for the ground state. And we had a set of variables, x1, x2, up to some xn. And now I'm skipping the quantum numbers because I'm assuming that all the single particle slots up to slot n are filled with n particles. So that means that compared to what we had previously, we included also additional quantum numbers. But now I'm simply setting up this Slater determinant with a state 1, and we have particle 1 here, a state 2. This is still particle 1, so the columns are for the particles, and then the rows are for the states they can fill. So we are filling all the states up to the Fermi level. So this 1 up to n are simply single particle states, as we introduced earlier, this kind of numbering. So this n, uppercase n here, is not only the number of particles, but it also defines where the Fermi level is. And then we have a phi of 1, x2, and this goes all the way up to particle n. And this goes all the way down to slot n and particle n. And this was a Slater determinant. Now, what we also had, we assume that this basis we have started with is an orthonormal basis. So we have an O and B basis, single particle basis, and that entails that the integral over one of these states as a function of x, of j, of x, is simply equal to delta ij. Now, what we do now in variational calculus, there are many ways of thinking of how we can vary this wave function. And the different strategies lead to different algorithms. The algorithm or the strategy which I'm going to show you here serves only in these lectures as an intermediate step, because for the practical algorithm, we're actually not going to vary these single particle wave functions, but we are going to vary the coefficients, because that gives a tractable, a better tractable numerical algorithm for solving the equations. But we are coming back to that. So now I just wanted to go through the basic philosophy first. So when we introduce variational calculus now, it's normal to assume that the endpoints are fixed, but then that the wave function which we are looking at, this phi of I of x, changes now, and the first term is just a normalization constant, because now we have a new wave function. And this wave function changes now to its original one plus some delta phi of I of x. And then we need to define what this one is. And in this specific case, we can now assume that this I is smaller or equal to the states up to the Fermi level, which we also labeled as an n here. Now, you can define this delta phi of I as you want, okay? So what you could do now is simply to say that this delta phi of I is now given by a parameter eta multiplied with a phi of A of x. And this A is now larger than the Fermi level. So we are assuming now that we are mixing in some components from a state above the Fermi level. So this is just an assumption we are making about this change in the wave function. Now, we know one thing is that the phi of A and phi of I, they are orthogonal to each other. So when we now calculate the normalization factor, So if we want this norm, then what we would typically have then is that this ni inverse squared, because we want the norm, we want the norm to be 1, so we have 1 over n squared. If you go back to the equation here, when we calculate the norm. So this is simply equal to a d of x, and then I would have a phi of I. And now I'm a little bit sloppy. I'm going to skip the x dependence on phi. And then we have, so this parameter eta can be a complex parameter. It doesn't need to be a real number, because the wave function itself is also an object which can be complex. So there are some cases where we have real wave functions, but in general, the wave function is a complex quantity. So it has a real part and an imaginary part. And this is now given by complex conjugate, and then it's multiplied with phi of I plus eta times phi of I. And if we write this out, this is simply equal to 1 plus eta squared. Because when we look at the cross terms with phi of alpha and phi of I, due to the orthonormality of the states, the cross terms, which only include eta and phi of I and phi of alpha of A, has to be equal to 0, these cross terms. Okay? So if we now look at the norm in terms of a linear dependence on eta, then we can say that n of I is proportional to 1 at linear order in eta. Now, we will normally assume that eta is a small perturbation of the wave function. So that means that the normal assumption is that this eta is much, much smaller than 1. That's the basic assumption we are making. So we are looking at a small perturbation. So when we do these calculations now, what happens when we make these changes? So these are changes we would make on all the single particle wave functions, which we have in the definition of the Slater determinant. So that means that this Slater determinant, which we put up in the beginning here, this Slater determinant is now going to change to a new one. And now I'm simply going to put a label Hartree-Fock on it, plus some eta, and then I have a change in this function, this Hartree-Fock function, and I haven't defined this change yet. So let's keep it very general here, okay? Now, if I now look at the energy of the ground state, this is an energy which I now have to calculate with this new wave function. So there's going to be a term, which is phi 0, h of f of h. This is the Hamiltonian we have of phi 0 Hartree-Fock here. And then I get a new term, which now contains linear terms in eta. So there's a complex conjugate term. And then I have a delta phi 0 Hartree-Fock of h of phi 0 Hartree-Fock. So this is a new Slater determinant we are actually including here. And then we have plus and eta. So I'm simply just plugging in the wave function and calculate the new expectation value. And then we have a phi 0 Hartree-Fock. And then we have an h of delta phi 0 Hartree-Fock. So this is the linear term in eta. And then we have a term which is quadratic in eta. Now, what is common to do when you do variational calculus is that you skip the quadratic term, because you assume that eta is very small, so that you can actually leave out the quadratic term. So since we assume that eta is very small, we leave out the quadratic term. So that gives us a term which we define as a variation in the expectation value of the energy, with that, the Hartree-Fock quantity. So what we have then, we can define something which we call E0 Hartree-Fock, which is then given by these two terms. Plus an eta, and then I have phi 0, Hartree-Fock, H0, delta phi 0, Hartree-Fock. Now, and what we want is to optimize this term so that this term is 0. So in the optimization, we want actually delta E0 as a function of this quantity eta to be equal to 0. That's what we want to have. Now, there's one thing I'm going to leave as a small exercise, and that is, if I give you the kind of information which you need, if you look at eta, this is going to have a real component of eta plus an imaginary component times I of eta. And then H is also assumed to be Hermitian. And I leave that as a small exercise to show that you can actually solve two equations separately. They lead to the same type of results. So you can either take the derivative with respect to eta complex conjugate or just with eta. So this is something which, with this information here, 1 and 2, you can then actually show that when eta is arbitrarily small, then you can either solve this problem, phi 0 Hartree-Fock of H of phi 0 Hartree-Fock equal to 0. Or alternatively, you can solve the problem delta phi 0. So it means that whether we solve for the complex conjugate eta or for the other one, we get two independent equations of each other. Yeah.
Point number one, then, what did you say that eta equals statement? What was the point of that statement?
That's complex conjugate. So this eta is complex conjugate.
What did the complex conjugate?
No, this is the so this is actually the eta, which would have a minus im of eta.
Okay.
So, but you can show that these two equations are independent of each other, so you can solve either one or the other one. And the thing you need then is actually to use this information here. So if you can then look at the real part of the equations, which means that if you look at the expectation values which are taking here, you can then actually show that this term here is 0, but this term here is also 0 when you vary eta.
Sorry, one more time. You're saying that eta is...
Eta is a parameter. That is your change in the wave function. Yeah. So you can get, when you optimize here, you can either optimize with respect to that one, or you can optimize with respect to this one. Because you're going to take the variational derivative of, so what you want now is a delta E0 of HF. So the derivative of this quantity with, or you take the whole energy with respect to either this one or that one. So this is what you take the derivative of. This is your actual change in the wave function. And you are going to take the derivative or the variational derivative with respect to these parameters. So if you go back to the full equation for the energy, what you have is this term here, plus these terms. And what you want is actually to take the derivative of E of the whole energy with respect to either this one or this one. So the first term does not depend, this one does not depend on eta, or this eta complex conjugate, or eta. But then you have two terms here. Now, these terms, whether you take the derivative with respect to this one or that one, you get either this equation to solve or this equation to solve. And they are independent of each other. So you can either look at this one or you can look at that one. And they're going to give you the same result. And that follows from the hermeticity of the problem as well. So you can see that if you plug in this one, and I leave that as a small exercise, you can then show that when you calculate this one or that one, you can get two equations which are independent of each other. And one of them is this, and the other one is that one. There's more information in the lecture notes, if you're not fully convinced here. Okay, so what I want to do now, so in the lecture notes, what I have is with Lagrangian multipliers, I do the derivations of these equations. But the problem with the equations in coordinate space is that you end up with an equation which contains a second derivative plus integrals. And numerically, this is called an integral differential set of equations. And these are normally more difficult to solve than the equations which we end up with if we vary the coefficients in front of the wave function. And this is the approach which is normally used in all practical implementations of the Hartree-Fock method. And this is what we are going to look at after the break. But first now, we are going to translate what you saw here, this small change. We are going to translate this one into a second quantized picture. So what you see here is one way you can think of the change in the wave function. So you bring in a piece which is not included in the original Slater determinant in these states here. This piece is obviously orthogonal to the basic function you had before. Yeah. What is? So this is the norm, because we have a norm in front here, and you want to normalize this quantity. And when you calculate the norm, since phi of A is orthogonal to phi of I, then the cross terms here with the with the eta here. So this cross term with that one multiplied with that one gives you 0 due to orthogonality. And then the norm is equal to 1 plus eta squared. And if you think of this at linear than eta, then, and since eta is much, much smaller than 1, then you can say that this norm is close to 1. But there is something which is slightly different from 1. So the assumption is that you make a very small perturbation of the state you have by mixing in contributions from states above the Fermi level. These states obviously have to have the same symmetry, but they will be orthogonal. So how does this translate into second quantization? So let's just do that before we look at the practical recipe for finding these new wave functions. So if we go to second quantization, what we can do then, if we now assume that we have a Hartree-Fock Slater determinant, this is obviously given in second quantization. We now act on the true vacuum state with these creation operators. Then we are looking at a variation. So we have a variation where now the variation is given by the inclusion of a one particle, one hole excitation. Because if you go back to what we did here, this ansatz or this specific choice, this means that we are now allowing for an admixture of a state above the Fermi level. So in second quantization, we can now represent this in the following way. So we can now have a delta phi 0 Hartree-Fock, which is equal to this parameter eta we had before, the small variation, and then we mix in a particle Hall state. So we are removing a particle from the state I, and we are promoting it to the state A. And then we have just a small change here. So this is the second quantized equivalent of what we did in the traditional first quantization or coordinate space representation. Okay. Now, what does that mean? So if we now just take the general equations, which we want to drive to zero, of H of phi 0 Hartree-Fock, now we can use the whole machinery with Wick's theorem and the rewritten operator for the energy with respect to a new vacuum state. So what does that mean? So this means for us now that what we have to set to zero is this term, which looks like this now. So we have a an eta, sorry. And then we have a AI of AA acting on the Hamiltonian. And then we have this phi 0 Hartree-Fock. And we want to drive this one to zero. And eta is not zero. So the term, yeah? Yeah, because now this is the, it's a Hermitian conjugate, yeah, yeah. So then we remember now that this H is something which is given in terms of the reference energy, which is just a constant. And that means that since we now are creating a one particle, one Hall state, the first term has to give zero. And then we had the one body operator with respect to the new vacuum, plus the two body operator. That's the Hamiltonian. So the first term with this constant, this E0 reference energy, that gives us just zero, because we have simply a constant which comes in here. And then this is a state with zero particle, zero hole excitations, whereas this is now a state with a one particle, one hole excitation. So that means that that first term is zero. So if we now just go back and look at what we had done before, so let's now take the term with the f of n, and let's skip the term eta. We don't need to look at that one. So what we would have then is simply this expectation value. So we have an A of A, and A of I, and then we have the sum over P and Q, and then we have this P, the matrix elements of this operator F, which I'm going to set up again. And then we have the operator AP dagger, AQ, and then we have a phi 0 Hartree-Fock.
So can we go to the previous page?
Yeah.
When you explain it,
yeah.
For the
Yeah.
That also
yeah, that should be also, sorry, I forgot that one. Thanks. That's correct. Yes. So you can solve it with respect to that one, or you can take the other equation. You will just get basically the same type of equations, similar types of equations. Now, if you now look at what you have here, this one is something which we now can only contract in one specific way. The only non-zero contractions are these two here. So that means that this gives us a term which is given by A of f of I, which is the same as A of H0 of I plus this sum which runs over all the states up to the Fermi level of I, A, J, of V of I, J, and this is an anti-symmetrized matrix element. And we want that one to be 0. Okay? You can do the other case. So if I take eta times phi 0 Hartree-Fock of H of delta phi 0 Hartree-Fock, if you do that one, and you put that one to 0, that is going to be the same as I of f of A equal to 0. Now, we are assuming that these are Hermitian operators. So they should, in principle, give us the same answers. So it's irrespective whether we vary with respect to eta complex conjugate or with eta. So what you see now is that this is nothing but what we are saying now, if we go back to FCI, so let's just quickly switch back to FCI. This is the same as saying that if we perform this variation, it means that we are taking this block with H and the one particle, one hole states, and we are putting that one to 0. But we have to be a little bit careful because this is not identical to a standard similarity transformation of your Hamiltonian. This is a specific choice, and we're coming back to that. Because you could say now, okay, if I now take my Hamiltonian and somebody gives me a special unitary transformation, which zeroes out this matrix element, it's not necessarily exactly equal to. In principle, it does the same thing for us, but it is not necessarily exactly equal, because if you take an algorithm like Householder's tridiagonalization method, which brings the matrix into a tridiagonal form, and then you find the eigenvalues afterwards, that may give you slightly different matrix elements compared to what you would get with Hartree-Fock. And I'm going to try to explain to you that you may not get exactly the same answers because you choose a specific recipe for implementing these equations. So what you're doing now, you're forcing this one to be 0, and you're forcing this one to be 0. But then you have to make a choice on the diagonal elements. So let's see, let's just quickly remind ourselves of FCI. So when we did FCI, we had the original Hamiltonian matrix. Hamiltonian matrix. And in that specific case, what we had, if we now just stick to a two-body interaction, so we had the one particle, one hole block, we have the two particle, two hole block, free particle, free hole, etc., up to n particle, n hole. And then we have the same here, phi 0. We have a one particle, one hole block, a two particle, two hole block. So these are many body states. And this goes all the way down to n particle, n hole. And then we set up the matrix here. Then we have matrix elements here, here, here. And since we have only a two-body interaction, all the rest of the matrix elements are 0. And then we have 0, down, and then we have x, x, x. So x are blocks now of matrix elements, which are not necessarily 0, etc. Now, when we now perform this Hartree-Fock or this optimization, where we change only a single particle wave function, what it means is that we are finding a transformation where we now transform the matrix. So let's call this U Hartree-Fock. So we perform a similarity transformation of our Hamiltonian matrix. And I'm going to put a hat here to indicate that this is the Hamiltonian matrix. This gives us now a matrix which looks like this. So I'm going to have some change matrix elements here. I'm going to have a 0 here, change matrix element, and these stay 0. So there is some kind of transformation we can make now, where we now can change these matrix elements, and this will be non-zero, this will be non-zero, but then this becomes 0, and then it just continues like this. Now, when we do the Hartree-Fock, when we implement the Hartree-Fock method and compare that with a diagonalization algorithm, so you could think of doing Jacobi's method, which I will come back to after the break, then that may not give you exactly the same equation. So let me try to explain to you why, even though the effect is the same, because we are putting this block equal to 0. So remember now that this specific block here means that these matrix elements are 0. And this is what we find here if we drive these terms here to 0. Because that matrix element, which we have here, is simply given by either this one or that one. Okay? So in the Hartree-Fock method, we make a choice. In order to satisfy that equation. So what we assume now is that we can find between two states, P, and this operator F and Q, this is equal to some epsilon P, and we call this Hartree-Fock now because this is linked with the Hartree-Fock recipe. And we call this, we give this simply an additional term, which is a Kronecker delta. So what we are having then is that if I now have a whole state and a particle state, this is also equal to A of F of I equal to 0. But then I have made a specific choice now, which allows me to implement this condition on that matrix elements. But I made a choice now where I require that this F acts like a one-body operator and has eigenstates and eigenvalues. So that means that what I'm saying here is that this, the action of F on a state I, is now the same as us having defined a new operator, which has this new basis as an eigenbasis. So what I'm requiring now is that F acting on a state P is now equal to some eigenstate, eigenenergy, multiplied with an eigenstate. And then I simply call this F, not an arrow, not an implication sign, but an arrow. This becomes now the Hartree-Fock operator. So that means that my H Hartree-Fock acting on a state P, and if I take this Q here, this is the same as us calculating Q of H0 times P plus Q, so H0 is the original one, and these new basis functions are not necessarily eigenstates of H0, as we had in our previous case. But they are eigenstates of this new operator. And that means that I now have a U Hartree-Fock, which acts on the state P, and this U Hartree-Fock, this term here, is nothing but the sum of all states below the Fermi level, Q of J of V of P of J anti-symmetrized. Now, this is a choice we can make in order to fulfill these expressions. But you know, there are many other ways you can do it, okay? But this becomes very convenient because it gives us a set of equations to solve, which mean that we solve one particle problems. So this is a one body problem, which you see here. We get a modified single particle energies. You're acting on a single particle state, but this single particle state gets its motion modified from the original operator, which contained, so this operator here has kinetic energy, which we often write like a T. So these are operators, plus some U external, which could be a confining potential like a harmonic oscillator, or the potentials which arises due to the atomic nucleus, which confines the motion of an electron in, let's say, a standard atom. And then what we are doing now is that we are modifying this motion by correcting it due to the presence of all the particles which occupy the states below the Fermi level. So this is normally called a mean field, which is being set up, and a mean field which reflects the medium you're having. So you're bringing in information of the specific system which you're dealing with. And that specific system gives what we would call a density dependence, because it depends on the density of states in that system. So you will often see this referred as a mean field or density dependent corrections. And the normal word is actually mean field. So you see the kind of links you can make with FCI. We make a specific choice, and after the break, I will show you a simple example with Jacobi's method, when you have only one particle, one whole state, and one ground state, which means that you have a 2 by 2, this would be then a 2 by 2 matrix. And then you can see that a standard diagonalization method is not necessarily equal to what we have chosen here. So what we have chosen here leads also to an efficient algorithm for solving the problem. I hope all these words here can help you in seeing, that's what I normally call the wood for the trees. Okay. And there's a very intuitive physical way of thinking in terms of particle hole excitations. And second quantization is something which allows us to, to say that, okay, Hartree-Fock now is the same as mixing in one particle, one hole excitations only. And if you can solve these equations, and life consists only of the ground state and one particle hole excitations, if you have such a Hilbert space, then you can actually solve the many-body problem exactly. Because then with a Hartree-Fock, you have only these Hamiltonian matrix, and with the Hartree-Fock transformation, you can read off the energies immediately. Okay. Hope that sounds a little bit clear. So we are using the variational theorem, or no, sorry, variational calculus. And what we end up with then is an equation of this type, which you see here. And that gives us a practical recipe where we make a choice, which then fulfills the conditions from variational calculus, but it gives us something more in addition. Before the break, what we did then was to take a step back and look at the connection with FCI. And in FCI, you could now think of this as finding a similarity transformation, which zeroes out the coupling between the ground state ansatz and all one particle, one hole excitations. Now, the only thing which we have from variational calculus is that these matrix elements have to be zero. So that gives us from variational calculus, it gives us a choice in order to fulfill these conditions, which follow from this general case from variational calculus. Then one way to fulfill that is to assume now that these Qs and Ps are eigenstates of the operator F. And if we assume that, then this condition is fulfilled immediately. But we have an additional constraint on the states below the Fermi level and the states above the Fermi level, that these are actually eigenstates of that specific operator. So just to gain some kind of intuition about the difference between an FCI method and Hartree-Fock, if you just think of an ideal world where we only have one particle, one Hall state, and one ground state, then the Hamiltonian matrix would just be a matrix which has ground state to ground state expectation value. And then there's a transition from the ground state to the one. So one is a one particle, one Hall state. And then we're assuming that this is let's just assume that this is a real matrix and it's symmetric. So the matrix elements on the non-diagonal are the same. Now, if you think of a standard eigenvalue problem, the way you could solve it, there is a famous method, which is called Jacobi's method, which you probably have encountered. And in Jacobi's method, we would simply find what we call a similarity transformation in terms of rotations around an axis. So we have sine theta, cosine theta, and then we multiply the matrix H01, H01, H11, and then we multiply it with a new transformation, which is now the transpose of the previous one, sine theta of cosine theta. So this is a rotation around an axis, and what we want then is that this simply becomes a diagonal matrix where we can just read off the eigenvalues like this. So we choose the angle, and if you perform the multiplication here, what you get then, if you look at the non-diagonal terms, you get a cosine squared minus a sine squared, plus the difference between H00, the diagonal elements, times a cosine, so C and S are cosine and sines, and we want that to be 0. So these are the non-diagonal elements when you now perform the matrix multiplications. And then you simply want to find an angle which drives the non-diagonal elements to 0. And in that specific case, you can now define a constant, which is just H11 minus H00. And then you have a 2H10 or 01. And that means that you can define the angle in terms of tan theta, which is given by minus tau plus minus 1 plus tau squared. And that defines the angle theta. So you can define the angle theta from these non-diagonal and diagonal matrix elements. Now, Jacobi's method is extremely inefficient because it just zeroes out one non-diagonal matrix elements at a time. So if you have a 1,000 by 1,000 matrix, you have to actually do this at least 1,000 times. The problem, however, is with Jacobi's method has another drawback. It's actually matrix elements that put to 0 may become non-zero after a given number of iterations. So it's an easy to implement method, but what you see here is the important thing is that this is a specific transformation you make in order to zero out this particle Hall to ground state matrix elements. And if you go back to the FCI case here, when you perform a standard diagonalization, what you're doing then is actually to perform a series of such transformations. And in this case, you can say now that Hartree-Fock corresponds to doing that, but it is not mathematical equivalent in terms of the expressions which you get in order to do that. So if you look at these expressions we hard-coded here, this may not necessarily give you exactly the same transformations which you have when you use a standard eigenvalue solver. But in principle, you are doing the same. So Hartree-Fock, yeah? The householder transformation, what that does is that it takes a matrix and transforms that one to a three-diagonal matrix, which is easier to diagonalize with Jacobi's method. So you take a dense matrix and you transform that with a finite number of transformations to a three-diagonal matrix. So that's what Householder does on a symmetric matrix. So that's one of the methods you would use when you take a large matrix, because Jacobi's method is normally inefficient. But you see now that's not the same. Now, before we now set up the recipe, what I wanted to give you are some interpretations of Hartree-Fock. Okay? So let's look at that before we look at the equations which we are ending up with coding. So let's look at interpretations, because that's also useful. And the thing is that it gives us, in certain cases, it gives us actually a decent first approximations which you can link with experiment. And that's extremely useful. So one thing which you can do now, we make an assumption here. So we are going to look at the system, let's say from atomic physics. And we are going to look at the system where we are calculating the energy with a given Hartree-Fock basis. So I'm just writing this as a phi 0. I'm assuming that's a Hartree-Fock basis, and I'm not going to put a superscript Hartree-Fock simply because I want to avoid all this clutter with names, okay? But now we're assuming that this is a calculation we run for n particles, okay? And then we know that the energy, so this energy, the expectation value of one Slater determinant is always the same, irrespective of basis. So that expectation value is something which goes back to what we did in the very beginning. So we would have a sum over I, H0 of I, plus the sum of Ij of V, Ij. And now I'm leaving out the anti-symmetrized subscript, just to avoid all this kind of clutter, okay? So these are anti-symmetrized matrix elements now. Then I'm going to make a pretty rough assumption. So the assumption now is that if I remove, so think of this as an atom like sodium. So sodium has 11 electrons. So what I do now, I remove one electron, but I make an assumption. So I remove below the Fermi level, electron K, electron in state K. Now there is a pretty important approximation I'm making. So it's still a sum I less than F, but I is different from K. And then I have I, H0 of I, plus 1/2. And now I have a double sum, again, Ij, and I is different from K, and J is different from K. And then I have my Ij, V of Ij. So I made an assumption here. Can you see what kind of assumption I've made? So think of you now solving the Hartree-Fock problem for n particles and n-1 particles. So what kind of assumption have I made here? If you look at the equations, and the I's and J's are the same in both cases. So suppose you can solve the Hartree-Fock equation for n-1 and n particles. In principle, these states, I and J, should be different because they have a different medium. So when I solve the equations with 10 particles or 11 particles, in principle, the states I get should be slightly different. Now, if I do atomic physics, we are thinking in terms of degrees of freedom of electrons. This means that the atomic nucleus stays unchanged. The atomic nucleus consists of protons and neutrons, and the protons give rise to the charge and is a dominating contribution to the total energy. So the contribution from the atomic nucleus is reflected in this term H0. So the assumption we are making now is that removing one electron doesn't modify the field the other electrons see. So this is an assumption. And it leads to something which is called Koopman's theorem, which is actually not a theorem, but is based on a pretty rough assumption that the single particle basis, which you have when you solve an n particle problem and an n-1 particle problem, is unchanged. This is the only way you can do what comes now. Because if I take the difference between these energies, so if I now take this difference, obviously the equations which you're going to see now, I could never get these if I didn't assume that the single particle basis is left unchanged by removing one particle. So that is an approximation, okay? Now you can then, when you do the algebra then, you will obviously have a term here where you have one less. So that means that if I take this term minus this term here, I'm going to get from the first term, I will simply get K of H0 of K, right? That's the first term because K is included here, but it's not included here. The rest is the same. Then, if I now take out the single particle energies, what I'm going to get then is, if I take out the single particle states from the double sum here, I will have one occasion where I has to be taken care of when I take here, so K is included in I. And then there's another case where K is included in J. So I'm going to get two terms, one with a half and then another one with a half. And then since these are just dummy variables, I can bring them together. And what I get then, when I bring everything together, I get simply a sum over J less than F. And then I have K of J of V of K of J. And what is this? This is actually the epsilon K Hartree-Fock. So if we think of atomic sodium, that has 11 electrons. And the way you can think of this now is as us removing one electron. So when you remove one, you have ionized sodium. So that has 10 electrons. So if somebody now can measure the ionization energy, that is the difference in energy between Na, natural sodium, minus ionized sodium. So if you have an experimental value for that, you can compare that directly with Hartree-Fock theory. And one of the initial successes of Hartree-Fock theory was since the interaction in between electrons in atomic physics is pretty weak compared to the contribution you get from H0, is that Hartree-Fock gave you a result which was pretty close to experiment. So this is normally called Koopman's theorem. I never like to call it a theorem because it's just you relating the differences between energies by assuming that the single particle states are unchanged when you remove one particle. You can do this for the addition of an electron. So if you add an electron to this system, then you're talking about the affinity energy. And if you do that, if I take now E, the difference between phi 0 of n plus 1 So I'm adding an electron, and then I look at this quantity here. Then this is going to be equal, if the energy, the state I add, then this is going to be given by the energy of a state above the Fermi level. So this is normally in atomic physics called the affinity energy. Now, since we have, this year, we have some nuclear physics aficionados, then let's now try to go to nuclear physics and see what happens there. Yeah. Yeah.
The assumption you're talking about,
yeah,
is that baked into the matrix elements there?
So I'm just forcing. I'm just saying now that I use the same single particle wave functions. So I do the calculation here, but then I use the same basis here. Alternatively, if you run a Hartree-Fock calculation, they will be slightly different. But what I'm assuming now is that this difference is not large. So I can go back and I can use the basis I found for the n particle system to calculate these matrix elements. So the single particle basis is unchanged, which means that the integrals are unchanged. But in principle, I should have calculated this system phi of n minus 1 again. Then I would have had an I tilde here and a j tilde. They would have been different. But now I'm simply running a calculation for one system, and then I'm applying this in here. Okay? So this is a gross approximation you make. Now, if we now go to nuclear physics, which is another case where you can actually relate a Hartree-Fock calculation to experimental data immediately. So the benefit here is that you can actually think of this as an approximation to something you can extract from experiment. So it's our first connection with experiment from a theory which is actually pretty simple. If we go to nuclear physics, there's something which is very well measured, and these are the masses of nuclei. And the masses of nuclei can then be used to define the binding energies. And this is a quantity which you can then use directly to compare your theory with. So in nuclear physics, there's something which is called BE, the binding energy of a given nucleus. So this could be a system. So A is the number of neutrons. So N is now the number of neutrons, not the number of particles, plus the number of protons. So this is something which we now are going to approximate with this Hartree-Fock calculation we run here of A. So we run a Hartree-Fock calculation for, and this could be a closed shell nucleus like oxygen 16. So you could think of your system and in oxygen 16, you have 8 protons and 8 neutrons. So this is one of the simple cases. So you have something which is called the 0p shell, the 0s shell for protons. So you can have 2 here and 6 here. So this defines your Fermi level. So you have 2 here and 6 here. And here comes your Fermi level. And then you have so-called particle states, as we have defined them. So the states below are normally sloppily referred as whole states, even if they are filled with particles. And this, the first one is 1s, 0d. And then you have higher shells here. So these would be the states above the Fermi level. Now, what you can do now is simply to assume that these Hartree-Fock calculations you run, these basis states, can now be used to calculate the binding energy of A minus 1. And that is something you can approximate then with the same Hartree-Fock calculations you did for the A particle case, but you're now using that one to calculate the Hartree-Fock energy with n-1 particles, but with the same basis states. You can also do this. You can add a particle of A plus 1 and simply just add a particle with the same basis. Now, if you then take the difference here between the binding energy of oxygen 16 minus the binding energy of oxygen 15, these are the experimental value. And now I am going to approximate them with the energy of a Hartree-Fock calculation, where I run a Hartree-Fock for oxygen 16, but then I use the same basis. So this is not a Hartree-Fock calculation for nitrogen 15, but I'm using that formula, which we put up earlier. Now, if I do that, this difference, which I have here, is going to be equal to the gap in energy between a state. So we take out this state here. And the last state here is actually what's labeled as a P1/2 state. This is a zero. This is the last state you have filled up. And since we now are removing a proton, this is going to be, in a Hartree-Fock sense, the single particle energy for a proton in the P1/2 state. I'm putting not Hartree-Fock here, but protons. So this is a proton state. And we would put a pi here to indicate that that's a proton. And this is the Hartree-Fock the result you would get from the Hartree-Fock calculation when you remove the last bound particle state here, so a whole state. And then you can do the same with additions of one particle. So you could look at the binding energy differences between oxygen 17 minus the binding energy of oxygen 16. And then you can find that this in a Hartree-Fock picture can be given by the D5 state, which is the first or the ground state of oxygen 17. And this is now a neutron. And this is the Hartree-Fock energy. So by using this Koopman's theorem, you can then find an estimate to experimental quantities. So this is something which links directly your theory with experiment. And clearly, in many of these type of calculations, you will often see that, especially for nuclear physics, this is a pretty gross approximation, assuming that the single particle basis is the same. You will often see that these Hartree-Fock energies don't relate well with experiment. But it's a very nice way of actually doing your first interpretations and link that with experiment. In atomic physics, this works pretty well. And so in atomic physics, what often happens is that a calculation with a mean field basis from Hartree-Fock does often a pretty good job in estimating the energies of, in particular, the ground state of the system. So you can often get something like 80 to 90% of the total correlation energy from Hartree-Fock, or of the total energy before you start adding more contributions. Yeah.
Is that because in atomic physics, the potential from the nucleus is much, much stronger? Like it contributes to
exactly.
Yeah.
So when you do an electron, a good fraction of the energy comes from this term here. Now, in nuclear physics, there is no confining potential. What binds nucleons together is the nuclear force. So in nuclear physics, in principle, this is just kinetic energy. So your effective potential then comes from the interaction between the particles. And that means that you could have expected that a kind of mean field approach doesn't make that much sense. But in general, nucleons keep their kind of individuality in a nucleus. Yeah.
But in nuclear symbol, you usually have a inert core, right?
Yeah.
Which may be interpreted as the static potential.
Yeah. But normally you have an effective Hamiltonian, which takes into account the effects of the core. So that's your many-body physics, which comes in, like through copper cluster theory, advanced many-body methods, where you bring in these additional correlations on top of a mean field, so that your effective Hamiltonian reflects the system you're looking at. So different physics gives obviously different approximations, but this kind of Hartree-Fock calculation gives us a pretty, how to say, a pretty easy way to link with experiment. And in atomic physics, this was a great success. Now, one thing I wanted to say now before we move on to the derivation of the practical algorithm is just a final word on the diagrammatic representation. Mathematic representation of Hartree-Fock. And what we have is now a matrix element of this type, or an integral, which is given by I of H Hartree-Fock of I. And the analytical expression runs like I of H0 of I, plus this term, which now contains an effect from the medium, where this is an anti-symmetrized matrix element. So in this case, we have the first one is simply now given by this whole state, which is a downgoing line, I and I here. And then we have a one-body operator, which we indicate with this cross. And then we have a new term where the summation over the states below the Fermi level is now represented by a closed loop. So what we had then, if we now look at the first term, so if we take this one, this is Ij, Vij minus Ij, Vji. So diagrammatically, this is represented by this term here. And then when we have a summation of a state, J, this is represented diagrammatically with a closed loop. But then we have an exchange term, which is then going to look like as follows. So I have now this J here, and then I have the initial whole state here, I. Sometimes you lump these together in an anti-symmetrized matrix element, which leads to what's called a Hugenholz diagram. And in that specific case, we would then bring together the vertices just into one dot here, and then we indicate the closed loop like this, J. Now, one thing you should keep in mind is that many people prefer this way of drawing the diagram. And if you go into the textbook by Shavit and Bartlett, this is normally the case. And in many, many cases, they actually, with this one, they mean this one. So instead of drawing both this one and that one, you just draw one diagram, but then you're assuming that this one also includes that. And that is, how to say, it's a recipe for chaos for the reader, because you have to know from the beginning what they actually mean. So some people tend to draw just one diagram because they don't want to deal with this kind of Hugenholz notation. Maybe they don't like it. Or there's something which just has become a practice in the community. But so the textbook of Shavit and Bartlett does this actually. And that can be somewhat confusing. Now then for the particle states, if we go back to that, so we have this one, A of F of A, and that one is now simply given by this particle state leaving and entering. We have the one body piece. And then we have the correction from the medium, the mean field. So we have a J, and an A, and an A. And then we have the exchange term. And it doesn't matter how you draw it, where you have A coming in here, and then you have J going like this, and A. You can just interchange it here because the matrix elements give you the same due to the symmetries. Then we have the final ones, which are these matrix elements which are 0. And they will also have a one-body term. So if we look at this case here, we would now have an incoming particle state and a leaving whole state, I. And then we have the next terms. So we would have this vertex here, I, AI, and then this bubble here, or tadpoles, as they often are called, because this looks like a tadpole, rumpetroll in Norwegian. So you will often see that as a name, actually, tadpole diagram. And then you have the final one here, where you have an incoming particle line, you have the income, and then the whole line here, and then you have a J here. And some people, again, would just write it like this, AI. So when you typically put labels on it, that means that you have performed all the contractions and you're looking at either a transition probability, a transition matrix elements, or an expectation value. So this would be the diagrammatic representation of Hartree-Fock. And in this specific case, these matrix elements sum to 0. But the other ones give us the eigen energies of that specific operator. I think we're going to stop here today because it will take me a little bit more time to go through the algorithm. Now, in the lecture notes, you will find the derivation of the integral differential equations if you look at the variations in coordinate space. But where we will start next week is to derive the Hartree-Fock equations by simply, so this is a topic where we begin next week, we are going to assume that this basis is now going to be given by these coefficients, Cp lambda of lambda, where lambda is the original basis. And then instead of varying this quantity, we are going to vary these coefficients. And that will give us a linear algebra problem with an eigenvalue problem, which we can diagonalize, but then we will solve it iteratively. And the reason for that is that we don't know this one, and we don't know that one. The only thing we know is this one. So we would start with a guess here. And then we would keep diagonalizing the matrix which we get till the single particle energies of these guys here don't change by more than a quantity you have defined. So you're going to get a set of nonlinear equations in the unknowns, which you will solve iteratively. This is much easier. So this variation in terms of the C's is much easier to solve numerically, and this is the standard way a Hartree-Fock calculation is done. Actually, it's so standard, if you ask ChatGPT to write a Hartree-Fock program for you, it does it. I actually tried it out, and I put it in the lecture notes. And it's written in a much nicer way than I would have written it. It makes life much easier, right? Because the mathematics, yeah, as long as you understand the mathematics properly, this is actually just a repeated diagonalization. So varying the coefficients is numerically easier than varying the shape of the wave function. Okay, so we started by a variation of the single particle wave functions. And that allows us to write everything in terms of one particle, one hole excitations. And we can link that with FCI as well. So this is where we start next week, guys. Enjoy your weekend.